Okay, now we have the exercise for the vector space, and we need to show this task. Is it a vector space or not? So I want to show you that Rn, I mean here that's Rn is x1, x2, x3, and x up to xn, which is the xe is a field of belong to real number. Yeah, is the real number. Is it a vector space? So it's the question. This Rn is a vector space or not? So if we talk about Rn, so it's mean to R and R factor two-dimensional, or R3 up to Rn. So by proving this Rn only, we can prove an etc. number of Rn factors. We can start with the cluster property of addition. Okay, we start with the number one. Okay, cluster property of addition. Okay, we have here the Rn, and the number one cluster is right that U plus V have to be the member of Rn, that it belongs to Rn. So you can take any number of U or any consistent number for U, and I will use the variable x and y here to help us to make it easier. So I'll take the U is x1, x2, x3 up to xn. That's the number of U, and V is y1, y2, y3 up to yn. After we have this one, so we have to input this number, this variable to U plus V. So we will get x1 plus y1, x2 plus y2, and x3 plus y3 up to xn plus yn. And okay, so you can see that this one is a member of, or it is closed for addition. Why? Because the answer of this one is against the same with U plus V or UV. Okay, so it's whole the first property. Okay, then we will do for the associative for the addition. Associative for addition. So for the associative for addition, we have we still use this term. We always use this term up to the end of this exercise. So I will always use U as x1, x2, x3, and up to xn, and V is y1, y2, y3 up to yn. So you have to remember that. And this associative property said that U plus V, it here in the bracket, plus W have to be same, or it will be U plus V, okay, plus W, but it moved the bracket to here. So we can write by using the same member of U and U factor and V factor here. We can write here x1, okay, sorry, x1 because the bracket in the first, so x1 plus y1 comma x2 plus y2 comma x3 plus y3 up to xn plus yn, and this is the bracket, and then plus we don't have a w factor unit first, so we will write for the w is z1, z2, or z3. So we have to be z1, z2, it's comma, z3, comma, up to zn. Then we can operate the associative addition for this, so it will be, we will make the x capital in the first, because we will move this u factor, which is x, have to be in the front of loan in the first term. So we'll write it x1 comma x2 comma x3 up to xn plus y1, okay, bracket, comma, plus z1 comma y2 plus z2 comma y3 plus z3 up to yn plus zn. So from this we can see that it is what is that? Okay, so you can see that it is the u plus yeah, and here is v plus w, v plus w. It is v, and it's w. So it is hold the associative for addition. Okay, and then okay, we have to move it first up, have to clean. Okay, and then we will start for other properties. Here is that commutative for addition, commutative for addition. Okay, in commutative for addition, it says that u plus v will be v plus u. So it still remains the member of u is x1, x2, and etc. It's also v, so we can directly write here x1 plus y1. I'm sorry, so I have to better to use the comma here. Okay, it's y1 comma x2 plus y2 comma x3 plus y3 and on to xn plus yn, or we can make it simple by substitute by switching this position and here to this place, because it's only the change or the switch of position, which is the first term move to the second term and the second term move to the first term. So it will be same y1 x1 plus x1 comma y2 plus x2 comma y3 plus x3 and yn plus xn. So it's proved that the v plus u, also you can see here it's hold what? Holds the commutative for addition property. Okay, then next we will prove the existence of identity element in addition. Identity element of addition. So what is identity element for addition? It means 0. So u plus 0, it have to be 0 plus u, and it will be u. Okay, so we will try to prove this u plus 0. It will be still remember u is x1, x2, x3 and xn plus 0, 0, 0, 0, 0, yeah, even indefinite. For 0 it only stay at 0, and then you will have x1 plus 0, and then x2 plus 0, x3 plus 0, and x4 plus 0. So it will be x1, x2, x3, and xn. So what it is? It is the factor of u. So we have proved this one. U plus 0 is 0. By using the same method, you can switch this to the first term in this one, to the second term, and you will get the same answer, because the movement is around here. It will move to x, x1, and 0, x2, 0, x3, and you will get the same u, the value. And then next, okay, so the next, okay, for the next we will prove for the inverse of metric addition. So the inverse of metric addition, they have property inverse of metric of addition. Sorry, it's not a metric. And the property said like this: u plus negative u, it will be 0, or negative u plus u. Okay, so it also have the 0. It will be 0. So we can take here for negative u, you have x1, x2, x3, and xn up to xn, and we can plus with the negative x1, negative x2, negative x3, up to negative xn, and we can gather the first term, second, it will be x1 minus x1, x2 minus x2, and x3 minus x3, up to xn minus xn. So it will be 0, 0, 0, 0. So what is this? It will be 0. Proved. And it's whole. Other properties. The other properties is a distributive for scalar. Distributive for scalar. Distributive for scalar. Distributive for scalar. Here the property says that if you have an alpha times u plus v, it will be alpha u plus alpha v. So you can enter the same factor of u and v, xy, x1 and y1. So we can say alpha, okay, xy, x2, x3, x4, up to xn, plus y1, y2, y3, and yn, or you can make it together x1 plus y1, and x2 plus y2, x3 plus y3, then so on plus yn. So you can multiply this. You can multiply this alpha x1. I'm sorry. Alpha x1 and plus alpha y1. Okay. Plus alpha x2 plus alpha y2. and x1 up to alpha xn plus yn, and then we will have the alpha x1. Okay, we will spread this one with this one, so we gather the x factor here, the member of the u factor together in the first term, so it will be alpha x1, alpha x2, alpha x3 up to alpha xn plus alpha y1, alpha y2, and alpha yn. So what this? So we have proved that this it will be same like this one. Is that it will be the same, but alpha u plus alpha v. Okay, so it means the holds the distributive for scalar, and then we will continue to the next. The next is that multiplication over addition. So multiplication for addition. In the multiplication of addition, it mentioned that alpha plus beta alpha plus beta times u, it will be alpha u plus beta u. Okay, so we still prove as usual. We can write the alpha plus beta here, and we introduce the x1, x2, comma x3 up to xn. Then we will do the operation of multiplication. So we will have this one, alpha beta plus beta x1, alpha plus beta x1, comma alpha plus beta x2, comma alpha plus beta x3, comma. Okay, and so on up to alpha beta xn. Then after that we can make a gather between the alpha x and b, the beta together with the beta. So we can write the alpha x1, comma alpha x1, alpha x2, comma alpha x3, and up to alpha xn plus beta x1 plus comma beta x2, and so on, beta xn. So if you see, that's u, and c u, so we can write this as alpha u plus beta u. So it means it holds what? Holds the multiplication for addition properties. Okay, then next we still have the associative multiplication for scalar multiplication. So associative for scalar multiplication. For the scalar multiplication, it's right that if a or alpha beta in the bracket times u, it will be gain same alpha beta u. Okay, right. This is the properties of the associative for scalar multiplication. So we only need to prove this. Yeah, we can write the u, still same u is alpha beta, and the u is x1, x2, comma, x3, comma, xn. Yeah, xn. Then we have to multiply alpha, beta, sorry, this one is a bracket, alpha, beta, x1, then alpha, beta, x2, comma, alpha, beta, x3, sorry, comma, alpha, beta, xn. And then we can change this terms to be alpha, so we can make it out from the bracket actually. So this one we try to move it from the bracket, so we write the alpha, beta, x1, so it will be the same, alpha, beta, x1, right? Alpha, beta, x1, it means alpha times beta, x1, beta, x2, beta, x3, up to beta, xn. So this is the alpha, b, beta, u. Okay, I'm sorry. So this is the alpha, beta, u, and it is proved. Yeah, you see, it's the result of this one. So it's in that it is holds for the associative for scalar multiplication properties. And then I hope this is the last one. This the identity element for scalar multiplication. So what is the identity element for scalar multiplication? It's number 1. So that's the property, right, that 1 or identity element of times u, it will be u. You can write here 1, 1, 1, 1, or sorry, I hope that it can be easier directly. We write 1 on the in front of as a scalar. Sorry, because it is a scalar, it's not a factor. So we only write 1 here. It's enough. x1, x2, x3 up to xn. Then we have 1 times x1, 1 times x2, 1 times x3 up to 1 times xn. So the result is x1, x2, x3, up to xn. So what it is look like? It's look like the member of factor u. Yeah, so it's the member of factor u. So identity element dot u is equal to u, and it is hold the identity element for scalar multiplication properties, and it's whole. So the answer is the Rn with the n tuples factor is the factor space, because it is holds all of the properties or the axioms of the factor space. Okay, thank you.